jointly hosted by Dassault Systems and Vias. Uh, so let me just briefly introduce myself. I am Swapan Sanjanwala. I have worked for 11 years for Dassault Systems, and now I'm a partner with Vias. I've focused specifically on the CPG industry, worked with many big clients on it, and also have extensive experience in the Dassault's SIMULIA software suite. So going forward, um, just to make sure that you can hear me, I just want to confirm that. So just give me a second. All right, yeah. So yeah, I just had a confirmation that that my voice is audible. Just wanted to confirm that. For just to kind of give kind of a brief kind of background. So as I mentioned, this is the second webinar in this series. So the first series we had about 2 weeks back. It was about overview of simulation and CPG. And in this second seminar, we are going to talk about the rigid packaging simulation, focusing more on the rigid structures. And in the subsequent seminar, we'll talk about flexible packaging and cartoon simulation and transportation. So just to give kind of a very quick overview of Vias, who we are. So we are a solution partner of Dassault Systems for SIMULIA Abacus, iSight, FESafe, Tosca, uh, Delmi, and Katia. And we have expertise across numerous industries, verticals, and our team consists of basically the PhDs and masters, all heavily grounded in abacus analysis. So I, I'll kind of jump into the 3ds perfect package industry solution. So so basically this is just a quick recap of the last seminar about what the 3D experience basically is. So the 3D experience, as in the last webinar, we had gone over it, and so the idea really is that it provides an integrated platform from the ideation, from the point you have your idea, to your CAD package, to if you do your artwork and labeling, and finally you have the perfect test where which is the focus of this webinar today, where you can evaluate the multiple the where you can evaluate the multiple loading scenarios even before physically testing it. And so we'll be focusing on the perfect test package and mainly on the rigid uh, simulations today. And so I wouldn't spend too much time on this today over here. So on the Simulia product portfolio, so so Simulia is a Dassault System brand for its simulation suite of products, and there is a bunch of tools we provide, which basically facilitates real life evaluation of simulations. So we have Abacus CAE, which is a front end preprocessor. We have 3D experience. We have the Abacus solvers, which are very powerful for the various simulation scenarios, and we'll see multiple examples of that. And so I wouldn't go too much in. Well, so we would go into the little bit into the details of this. So just as a recap from the first webinar, so what is specifically unique about applying simulation to consumer goods? So simulation has been applied to automobile, aerospace, and a number of industries, and it is fairly mature in the automobile and aerospace industries. I would say so, because if you think of an automotive and aerospace problem, you're modeling steel, aluminum, and things which wherein it is much more easier to define a material model and capture that material model. When you kind of put simulation to consumer products, there is a different set of challenges. One, you have to deal with material models which are highly nonlinear. You may not know the exact material properties. There might be time dependency, there is plasticity, there is hyperelasticity. Secondly, there is extremely high deformation, and often it is at the very edge of what can be addressed by the traditional methods. So it's been kind of a journey of decades with Simulia, where kind of we have mastered how to handle most of these. how to handle extreme deformation, highly nonlinear contact, complex physics, and also provide the framework for you to bring in your own physics, if necessary, whether it is co-simulation or whether it is your own material model. So this was a brief recap from the last one, and just as a kind of a proof, we have kind of a physical test on the left hand side and a virtual test. Now I can tell you that this problem is really difficult. We can see there is extreme deformation, there is self contact, and more importantly, if you look at the physical test versus the virtual test, how closely the results match. So, when you're looking at simulation, the number one thing here is what is the quality of the solver that you have, and how effective the solver is. And so Abacus has worked on this technology for a couple of decades, and it has a very, very powerful solver. Uh, all right. So again, the advantage of simulation. Very quickly, a recap. If you can simulate your manufacturing or your design before actually physically making it, you can obviously reduce your cost. You can evaluate many more ideas. You can, which may not be practically possible to evaluate it. If you can, if you have to do physical, of course you do need to do physical testing at the end of it, but you can kind of eliminate a few steps in between. Well, basically you can explore a number of ideas which may not be possible to do it when you're just doing physical testing. You cannot make hundreds and thousands of iterations to do it. All right, so let's jump into the rigid packaging scenarios. So the way I plan to cover it is that I will go over some of the topics which might be a recap from the last time, but in this seminar I'll keep the focus more on the demos where you can actually see the software in action. So so we have this capping analysis. You can simulate the capping analysis in a number of ways. How much would be the torque required to open the bottle, and so we can predict that. Yeah, and it could be a different kind of an opening scenario. It could be a hinge cap, so we can predict the stresses which are required when the opening and the closing phases, and the results and the stresses on the cap. Uh, if you really dig down into the simulation, if you have to, what we need here is also some kind of a method where we can specify the damage initiation criteria. Because if you're opening the cap the first time, what would be the force required? We can specify the damage initiation. We can model even from a fracture mechanics perspective. We can model the sealing analysis. We can model the stresses over here. So next, I would talk about the squeeze and the top loads. But what I would like to do different is we'll kind of go over an end-to-end kind of a little bit of the simulation. So again, kind of looking at the whole from a platform perspective. So we basically start with the bottle ideation. We have different ideas. You can capture those ideas in your sketches inside of CATIA, inside of Natural Sketch, which is an application in the 3D Experience platform. You can create your bottle with CAD in CATIA, and you can manage your all your parameters, all the CATIA knowledge parameters. You can parameterize that bottle geometry, which would allow for uh, a much higher flexibility in changing the geometry of the bottle. And once you have that, you can specify the simulation criteria. You can do your virtual testing for a variety of load cases and also optimize it. So we'll go over it. Bottle ideation. So we have a specific package for that, which can capture it. You can basically create sketches, ideas. You can capture those things, the new ideas into it. You can look up your past experience, and you can create the design models in CATIA, design 1, design 2, design 3. Let's say we created a few designs here, and we can then go ahead and create the parameters. Like there are 3 different sections here. What do we want to parameterize? Say, do we want the number of ribs as a variable? What would be the optimal number of ribs? What should be the ideal radius of the ribs? You can do that individually for each of the sections. And once we have the CAD model, once we've created the CAD parameters, we are ready to get into the simulation part of it. in the simulation part of it. So once we have the CAD model, so this simulation assumes that we have the CAD model, and I mean, so we created the CAD model in CATIA. One thing I would like to emphasize is that this is one integrated platform. So once you create your CAD model in CATIA, you have the CAD model in CATIA, you just switch to the simulation context. It's one platform, so there is the friction in transporting of files from CAD to simulation is absent here. And as a simulation analyst with many years of experience, I can say that that's for sure a kind of a game changer. I mean, the amount of time you would spend in repairing a geometry is kind of absent when you have this one integrated platform. So let's go over this simulation. So we have defined this different sections. We have these three sections in the bottle. We have basically created the parameters which we have allowed it. We have the three variations of the three sections. We have the radius of the ribs. We have the number of rib bottoms. So essentially, we have kind of parameterized the important things which we want, which we think which can impact the performance of the bottle. So the idea really is that, I mean, once you do this, you can very quickly go ahead and evaluate a number of scenarios and even perform this optimizations. So we can build inbuilt checks inside it, so that that is basically we have kind of creating the geometry here. We can build in the inbuilt checks here, so we know that we are not doing anything stupid. Actually, I'm sorry, that's the whole video is not playing up. Let me Okay, so just give me a second. All right, so we switch to the simulation context. Yeah, I'm sorry about that confusion. We select the uh, we select the structure. We give it a title. uh, Once we have the CAD, we switch to simulation context. We create a procedure step, and we switch to the content. We can switch to content. So we have the bottle which we created in CAD. We had the various parameters defined. Now our next job is going to be mesh the various sections, and we can specify different meshing rules for each of the sections. And the meshing capability in CATIA is pretty powerful. You can specify what meshes we want, what features you want to ignore, and so forth. And so once you change the geometry, those meshing rules are kind of automatically encapsulated. So once we have the mesh defined, we are going to define the material properties. And in the material properties, we are going to use the parameters which we had defined in a, that which we had defined earlier. So you can see that there is kind of a seamless, we can seamlessly use the CATIA parameters directly in the simulation. So there is kind of a seamless integration between CAD and simulation over here. So we have defined the various sets, what we call as publications, and we can apply the material properties for different sections, for each of the different sections separately. and specify maybe a different parameter for each one of them. So once we have the model completed, we can go ahead and apply the constraints. So since we want to apply top load, I'm going to define kinematic constraints at the top. So there are a number of ways you can approach it. You can create a plate and you can set, so it's just kind of a demonstration exercise right now. And we can define the regions. So the whole purpose of this is that how simply this can be addressed. So these things, how simply this can be addressed uh, within the 3D Experience platform. So we have the sets defined, and on those sets we define the groups, and we have the interactions. We can define the interactions here. We define the friction coefficient, define the contact property, the loads. So I'm going to go a little bit fast here just to, in the interest of time, because I have a lot of material. We apply the amplitude, and once we have that, we can step to the analysis. We define I'll skip some of the part. So we can define, we can basically look at, we can define the output variables of interest which we want to capture for post processing. And once we have that, we are good to run the simulation. And you know essentially iteration on this simulation would also be kind of very quick. So it's kind of, again, the key thing that I wanted to highlight is that there is a complete integration of CAD and finite element in this scenario. So I'll jump on in the interest of time for the next one. So so basically you can go one step further. We can apply rendering properties to each of the different sections, and we can really create a really realistic rendering based on the material properties and the on the rendering properties. So that's kind of outside the scope of simulation, but just wanted to kind of cover it about the advantages of having a one kind of comprehensive background. So next, so I want to go over a little bit on the creation of engineering templates. So this is the squeeze load scenario. So the idea behind engineering template is that right now we just saw that we created a simulation for top load. And what if we want to kind of templatize it? So the next time it's just not that particular bottle, but we want to bring in a completely different geometry. How simple it should be to repeat the whole steps. Can we create a template and can we bring it back? And that's basically the process that this video is about. We are going to create a template based on an existing simulation with a few clicks. So once we have a template, once we have a simulation, we can templatize that simulation, and we can say that what is variable in it, and what is variable. It need not be just the CAD parameters. It could be just be a different geometry that we are bringing in, right? So we are going to we specified the geometry over here. We specified the geometry and the simulation. As uh, we kind of reference to this template, the geometry in the simulation, and we're defining what at instantiation of the template, what geometry needs to be replaced in the simulation, and what are the properties that we need at instantiation. So we have the FEM top load and the squeeze load, kind of templates, basically templatized, and we have said that what is the behavior at instantiation. Do we want to duplicate it? And we can also specify that at like when we instantiate it, what are the parameters we want to be we want to vary. So if for a particular geometry we want a different load, the load can be a parameter. And so once we at the point we at the point we instantiate it, that would be a variable. If material property is a parameter from a list of material properties, that could be a parameter. So the idea really is that this this what this uh, does is that this enables automation, not just for a particular bottle with parameters, but across a range of bottles. So once we have created a template, we bring in our new geometry for design import and preparation. We can search for past existing geometries, and the 3D experience platform, it involves CATIA, SolidWorks. So if we have created, we could also store instructions related to the template, and so somebody could, you can basically go and search for, likewise, for the templates which are applicable to your work, open instruction documents and see what, if there is any specific instructions that need to be followed for using that particular template. And in this case, okay, so there are a few things which need to be taken care of. One is that the template expects that the name of the regions are kind of clearly identified, and that is kind of basically captured here in this document. So by that regions, we what we call as publications in over here. So we define the regions for a completely different model geometry, and once those regions are defined, we are good to, we can go to the template, we browse to the template which we just created, and we paste the existing bottle in it, and basically, and the parameters which we have exposed. So the top load, the value of the top load which we had exposed, and once we have that, we are good with a top load scenario on a completely new different bottle geometry. So kind of this was an example of creating templates very quickly. So the whole idea of what I wanted to emphasize is that you have a workflow. It is kind of very easy to apply it to multiple scenarios and use cases for reusability. All right. So next, so we focused on squeeze top load. So we can also do for rigid structures, plastic injection, blow molding. So plastic injection, SIMULIA has a tool, SimpoE, which is integrated inside of our SolidWorks package. And the idea really is that you can, it's integrated with 3D Experience too, I'm sorry. And the idea really is that you can basically see uh, how the manufacturing process is going to affect the mold and vice versa, and avoid costly mold reworks. Blow molding, this was something which I covered the last time. The well, this one requires, it has high deformation. You need, what the solver needs is an ability to handle high deformation. It you the Well, the process itself can be quite complex, the material modeling part of it, and native to Abacus, we have a number of material properties. We have elasticity, we have hyperelasticity, we have plasticity. You can define finite strain elasticity and plasticity models coupled to each other. You have viscoelasticity, and also, if none of the material models which are native to the SIMULIA software is there, there is a framework by which you can go ahead and define your own material models in it. So, uh, you know, uh, on the blow molding piece, and then, talking of extreme deformation, if we really need to model a liquid flow, we can model that. We can model bottle fluid interaction. There are a number of ways which we can go about the simulation. So from abstraction, which is all encapsulated within the structural solver, to techniques which are progressively difficult, from spherical particle hydrodynamics, SPH method, the Eilevian domain, the Eilevian Lagrangian technique, or a fully coupled FSI technique. So I wouldn't go too much into the details of the techniques. What I would like to focus on is something which would be of interest to most of it. So I did kind of very briefly touch on this last time, but I want to go into this process into a little more detail. Uh, so essentially, if you want to reduce your material cost, that's what we call as lightweighting. Even if it's 5% reduction, if you're making billions of them, and that the actual cost savings could be significant. And we have had customers who do that. So here's a testimonial from MCall. So we are just kind of briefly going over this process, how that process would look like here. So we have the initial design, we have the what we have, the stretch blow molding. Here we start with the stretch blow molding, and from the with the stretch blow molding, we do that process inside of Abacus. We get the thickness profile. We can export the thickness profile, and we can get a top load. So this is all kind of, it's in the framework of what the demos we just did right now. And we get a top load. We get what would be the force required, what is the top load for it. And it turns out that, it's a little bit over designed. We can stay around the, our goal is to stay around the 100 mark, and I mean, we can go about and reduce the material. But how do we reduce the material? From where do we reduce the material? That can be guesswork, or we need tools to support that. And that's what the optimization sequence is about. So if we have the section thickness, we have the thickness profile, we have the initial preform thickness from the blow molding simulation, and we can take a simplistic approach where, okay, let me try a trial and error, and let me kind of reduce the thickness profile uniformly and see what comes around. And we can see that it's kind of gone quite fast. Just for a 25% reduction, the force the just for a 25% reduction in mass, the overall force reduced pretty significantly. So we got a 47% reduction here, and significantly higher stresses. So clearly we need a much more sophisticated technique. So what the platform provides is also a mechanism wherein you can define your optimization workflow completely. So over here, I mean, this is kind of a plug and play technology. So we have linkages, or what we call as adapters, or applications which are two different softwares, uh, and it necessarily is not restricted just to Abacus. It could be a different solver, it could be MATLAB. We have a library of those components. So we have this entire bottle optimization workflow we have defined here. So before I jump into the into this workflow, into the little bit of the details of the workflow, so what we have, we choose a number of parameters that we want to vary. We can decide what are the parameters we want to focus on. We have 5 thickness values as optimization parameters, and we have the constraint, that how much where what should be the minimum top load force. And our target is really, our optimization problem is really, we want to minimize our mass so that we have some cost savings. So we define the workflow here. We have the bottle design optimization workflow defined over here as a first step in so this would the optimization process would kind of iterate over a number of runs till we find a good solution. And it will basically, and we also have a choice of looking at it. So we'll kind of look into it. So we have the as a first step in the optimization, we do our blow molding, from where we get the thickness profile. We export that thickness profile and do our top load analysis. And from there, we get the force for the how much is the top load force. We do a criteria check, and the optimization algorithm kind of iterates on it till it gets a better answer. So here we see, like this were all the runs which are performed by the optimization algorithm automatically. So this could be a few hundred runs, it could be a few thousand runs, it could be 10 or 15 runs. So we can find out what is the best kind of what's the best target thickness, which will help us to kind of minimize the mass. And eventually, what we found is that we got a 43% reduction in mass, whereas still maintaining our top load criteria. So, I mean, this was just an example of the decision support part of it. So the really what we saved was a 17.8 grams, how much that mass corresponds to. And if you start multiplying the numbers, it can very quickly add up. All the numbers, not just from a material cost, but from the transportation cost, the fuel cost, the impact on environment, and so forth. So we can take this idea even further, the optimization idea even further, and do a full-blown reliability analysis on it. So I'll just kind of go with a couple of slides. I mean, I'll come back to that old slides. But the idea really would be that your design space looks something like this. There are areas where, which are kind of not viable, where you're going to violate your top load criteria, and you're looking for optimal solutions. Now, the optimal solutions usually end up being exactly near the constraint boundaries, just the very nature of the mathematical things. So on paper, that might look like a very good solution, but since your process always has some input variations, it could be the geometric tolerances, it could be the material properties, you always have those slight variations, and you can basically capture those variations in a statistical framework and give that as an input and do a full-blown reliability analysis here. So really, the optimal solution, though the optimal solution may come out to be here somewhere in this constraint boundary, you want to move it somewhere, in the middle. And where exactly to move it? What would be the ideal location to move it? So that, you can hit your reliability targets. So the reliability targets, the problem statement could be, I want only 3 of them to fail per million. And, we can basically pose this problem in within the within the tools that we have, and we can create a workflow. We can author a workflow where we do it. So the idea really in that workflow would be, we first do a design of experiments, which is a number of runs. We create a approximation model out of it. Once you create an approximation, you don't need to run your analysis over and over again. And so basically the idea really is that once you have a sufficient number of runs, yeah, you have a database of runs, and once you have that, you can create an empirical model out of those runs. And for the next set of iterations, if you change the parameters, you don't need to run the solver. It could be something as easy as getting it out of an Excel plugin. So once you're at that point, what we call as approximation, it goes by different names. You can call it response surface, you can call it surrogate modeling. Once you have that, you can do your further optimization, and you can define your reliability studies right on it. So you can do so. This kind of captures the workflow what we just talked about. You author your DOE, design of experiments, and you can incorporate multiple analysis in it. It need not just be your top load. It could be your optimization, uh, could incorporate maybe labeling, maybe your squeeze analysis, maybe your capping analysis, just to give an idea. And once you have your output from your design of experiments, you create an empirical model out of it, and then do a full-blown Six Sigma analysis, which has optimization built in on it, on the approximation which you just created. And a Six Sigma analysis typically would involve millions of runs. And the solvers here, this analysis can take a fair amount of time, depending upon how many CPUs you use, the complexity of the model, and so forth. But let's say it takes an hour, and if you want to do millions of them, it's not viable to do a full-blown solution in it. So in that scenario, you can do a Six Sigma optimization. I mean, once you have the approximation, you you need not use the solver. You are good to go directly. So again, to emphasize, so these you can do this all within one platform. That's kind of a change from what we used to do with the legacy platforms, and that makes it much more easier. So you have one 3D experience platform, and you have your compute resources within the company or on the cloud somewhere, and you solve it, the problem. Just to give an idea of other shape optimization example problems that have been solved successfully, if you want to stiffen your packaging container, what would be the optimum number of webs? So this was an example which has been applied successfully. Bead optimization, what would be the best number of beads for a particular stiffness? You want to do it. uh, you can apply it for shelf life. So the shelf life is, you have a carbonated bottle. It could be carbonated bottle, it could be wine. The idea really is to preserve fizz, and over time the fizz kind of fizzles out. So, I mean, basically, there's leakage of carbon dioxide to the atmosphere, and oxygen back into it. And there are two things which primarily impact that. Well, actually, a number of things impact that. How thick is your bottle? What is the material properties of your bottle? And what is your geometry profile? And even by changing the different profile, you can actually reduce your max stress. So if there is too much accumulation of pressure inside it, the bottle can explode. So you can, basically work. We can do the simulations over here. the gas diffusion simulations over here. You can also measure the creep strains, the creep pressure and creep value. So uh, over time, the stiffness of your material could be a function of the creep stress. We can capture that, and we can come up with a more accurate prediction of the shelf life. So I think we are kind of out of time. So I mean, just to kind of the sake of completeness, we can apply it to glass bottles. This need not be essentially be plastics. The material is really your choice, really. I mean, and what we can model. It can be glass. It could be various aluminum models. I mean, so I mean, it could be a metal modeling and metal can forming and so forth. So I mean, if there is interest in it, I'll be more than happy to have a just to have a one-to-one talk. And uh, I covered this last time, but just for the sake of completeness, since you're talking of rigid structures, you can apply it to assembly line. A classic example is of conveying. So this was applied on a process with on Procter and Gamble. And this was way back in 2002, and we have what we have is a video of the real simulation. I mean, of the real world and the simulation, and they kind of match up fairly closely. So we have a customer testimony about on jet packaging where where the customer has applied the where I mean where the plastic technologies inc. They had applied it very successfully on the uh, in order to reduce their material cost. And so just the kind of things we just talked about. And with this, I'll just open it up for questions. So any questions it may have, feel free to ask questions. So I can see one question here. Okay, so we have you can do a static analysis, with which you can do a dynamic analysis. We also have the Abacus explicit solver, which follows a different integration scheme from the Abacus solvers. I mean, from the implicit solvers. Uh, the advantage of explicit is that it can handle very high extent of deformation. And within the explicit solver, we have several sophisticated techniques to handle high deformation, like SPH, which is the spherical particle hydrodynamics. We have I live in Lagrangian framework, wherein you can treat your material as a fluid. We can also do a complete co-simulation. So we can do a complete co-simulation, and so basically by co-simulation imply that if you have a different fluid solvers, or if you want to use a fluid solver within Abacus to do so, we can do that. We can couple the structural and the fluid solvers together, and the fluid solver need not necessarily be, I mean, native to 3D experience. It could be something which you get your own solver. It could even be a competitive product. So basically, I mean, and that kind of applies to the whole kind of the physical scenarios. There could be parts of it where you would want to where where you want to uh, kind of say just I mean for there could be part of aspects of it where you want to use your own solver and not use a native Abacus solver for it. So if you have any questions, I would you can ask it over chat right now, or you could ask it uh, you can ask it in the Q&A section. Uh, so feel free to ask it in the Q&A section, or you could help me privately. I mean, you can ask it. I mean, eventually you can ask it privately. So uh, right. Okay, so I see that there has been a question asked by Pietro Gianbelli. I'm sorry if I mispronounce your name, but you could, I mean, well, right now it's not open for the attendees to speak directly. So if you have a question, I would request you to type it in the chat window, or we can talk one on one. So I would highly encourage you to just type it in the chat window so the others can benefit from it. Okay, so we had a question that can we calculate the life of a component? Yes, we can calculate the life of a component. So for calculating the life of a component, we have the FE-safe solver which Dassault had acquired, and you can basically, once you do one loading scenario, and if you provide a history of your loads, you can come up with what is an accurate assessment of the life of that particular component. So you can come up that whether this life is going to be 1 year, 3 years, or I mean, well, you can how many cycles the loading it's going to last, how many loading cycles histories is going to last. Is it going to be 400 loading cycles, 500 loading cycles? You can come up with that answers. Uh, so we have a question: have those capping model you shared earlier been validated or not? Yes, they have been validated. So really, what right seal pressure you use would depend on your use case. You could basically, I mean, basically you input the values what you have from your experimental data. You come up with your experimental values, and I mean, and you come up with that. I mean, basically you have your experimental data, and what you're trying to do is that you're trying to once you have experimental data, you try to create a physical simulation and try to see whether the experimental matches up with reality. So the other question we have is that does it have cloud integration? So part of the solver we do have cloud integration for the Abacus solver. We do also have a cloud integration for the 3D experience platform. For those who want to give this a try, they can give this a try for the platform a try. It's a lightweight way to give the cloud integration a try. So and we can provide the details of the cloud integration. If you want a demo account, we can work on it. If you want a trial account to try the software out, if you have a specific problem in mind, we can go over it. Uh, we can discuss that. So any other questions, anybody? If not, we will end this. And again, feel free if you have questions to just ping us, send us. Somebody would follow up with you. And it's just, I mean, if you have a problem where you think that this can be applied, if you want to do a proof of concept, we would be happy to work together and collaborate. Okay. So you can send your questions at support@vias.com. We would send this also by email. I mean, but if you, I mean, just to just for the sake of completeness, I'm just going to type that out at. All right. So basically, support@viascorp.com. If you have any questions, please feel free to send emails on that, or just give us a call. All right. It looks like we don't have any other questions, so I would end this over here. All right. Thank you.